What is up, Flutter devs? I recently published a package to PubDev, and I wanted to share some information about that with you for those of you that didn't hear. It's called Super Declarative Geometry. It's dedicated to kind of all things geometry, but for right now, it's primarily about angles, polar coordinates, and some mappings between polar coordinates and Cartesian coordinates. You might be wondering why I created such a package. Well, I've done a lot of user interfaces in Flutter that are kind of radial, dials and circular progress bars and things like this. And the nature of these interfaces is that inevitably you end up painting based on radial values, based on angles, 30 degrees here, 45 degrees there. But painting is always in terms of Cartesian coordinates. It's always in terms of XY values, even when you're dealing with angles and distances. So what if we had a package that made it easy to work with angles and distances? By the way, an angle plus a distance is a polar coordinate. So a package that supports angle manipulation and polar coordinate manipulation, that could go a long way into simplifying a lot of these radial user interfaces. That's the package that I set out to create. It's called Super Declarative Geometry. It's a pure Dart package. I believe very much in solving kind of pure mathematical or lower level non-UI problems at the Dart level, and then kind of building Flutter stuff on top of those solutions. So this is a pure Dart package. You could use it in a command line app. You could use it on the server if you wanted, but of course you could use it in Flutter. I thought I'd take a few minutes today to introduce you to that package, show you kind of what it does and why you might want to use it. So to get us started, I have on the screen here the PubDev listing. So if you make your way to this listing, you're in the right place. Again, it's called Super Declarative Geometry. At the time of this video, it's version 0.10. So I haven't put it at 1.0 yet because I want to see some people use it. I want to make sure the APIs are correct. I want to eliminate as many bugs as possible before we declare it 1.0. Let me survey this for you so you can get an idea of what we're talking about. First, in the README, I put a quick reference in here that has all these examples here of what you can do with this package. But let's just go through a little bit of it. Right off the bat, we're talking about angles. So typically, when you're working with angles in Dart or Flutter, what you have is just some double. And that double might represent degrees, it might represent radians, it might represent a percentage. And then everywhere through your code, you have to remember, is this radians, degrees, or percent? And then you have to convert between them. This is a big hassle. It can easily lead to a lot of bugs. So right here, notice that right off the bat, you can create an angle object either from degrees or from radians. And actually, I don't have it here in the quick reference, but you can even create an angle from a percentage. So very easy to create angles. And this does not produce a double, this produces an actual angle object. Angle is now a first-class citizen with this package that I've created. Once you've actually created an angle, if you want to get the degrees or radians back out, because of course Flutter does not understand the angle type. Flutter uses radians almost exclusively. So you can say myAngle.degrees to get the number of degrees back out. You can say myAngle.radians to get the radians back out. You can create from these, you can retrieve these, it's really easy. But there are a number of other kind of introspection capabilities that I've built here that it may not be obvious where to use them, but as you start doing things with angles, these questions just pop up. So for example, you can give it an angle, you can ask if it's positive or negative. That's very nice to have when you're working on dials. Similarly, you can take an angle, maybe it's positive, maybe it's negative, but you can force it into the positive version of itself. Now, when I say the positive version of itself, I mentioned that here in this little comment. If it's negative 270 degrees, it does not become positive 270 degrees. It becomes positive 90 degrees because negative 270 and positive 90 are equivalent angles, but it ensures that the version of the angle that you're using is positive. because when you're adding a bunch of angles together, if you throw a negative one in there, it might be a real problem. So you can force it to be positive. You can also force it to be negative. Also, given an angle, given how large an angle is, there are different terms to describe that angle in geometry. For example, you have acute angles, you have obtuse angles, and you have reflex angles. You can ask an angle if it is any one of those individually. So if you care about whether or not it's obtuse, you can say, hey, angle, are you obtuse? Now, you may also want to do a switch statement depending on which one of those it is. So you can ask an angle for its category, and category is either going to be acute, obtuse, or reflex. Okay, so you can kind of inspect these angles. We have angle equivalency. This is different than equals. So an angle of 90 degrees is only equal to another angle of 90 degrees, but an angle of 90 degrees is equivalent to an angle of negative 270 degrees, because though the actual measure is different, they point in the same direction. So this stuff goes on. I'll let you read over this. Rotation's an interesting thing to note here. Angles go from 0 degrees to essentially 359.999999 degrees. They do not go to 360, because if an angle went from 0 to 360, then we would have an ambiguity at 360. Is it 0 or is it 360? To avoid that, I do not allow angles to represent anything 360 or above. But you can, and that's with rotations. Rotations can have an angle of any size, 540, 720, any angle you want, 360, of course. So if you need to go beyond the limitations of angle, if you need more angle than an angle can give you, you have rotations. And then we get to the interesting part, which is polar coordinates. Polar coordinates, by their mathematical definition, are a combination of an angle and a distance. So you'll see that the constructor here takes a distance followed by an angle. And because it's in the geometry package, that angle is actually of type angle. And this here is a typo. This should say angle.from degrees. I'll need to fix that. But it takes a distance and it takes what should be an angle. But also you can create a polar coordinate from a Cartesian coordinate, an XY. So you pass in XY values and you get out a polar coordinate. This is how they become really useful for Flutter user interfaces. Flutter user interfaces are always painted with XY values, but the nature of your user interface, like a dial, radial progress, etc., might make a lot more sense in terms of angles and distance. Much like angles, polar coordinates can be added and subtracted. You can also multiply and divide by scalars. And similar to what I just said, you can map a polar coordinate to a Cartesian point. So here we have a polar coordinate, and we can call to Cartesian to get the Cartesian coordinate point. Now, this is a very simple example. It can get a bit more complicated because the Cartesian coordinate for a given polar coordinate is actually based on how you map between them. And that brings us, in fact, to this app that you see running over here on the iPhone simulator. This is the example app that comes with the super declarative geometry package, and it shows you essentially what a polar coordinate is. Notice down here at the bottom, it says polar coordinate 150 by 60 degrees. That means the length of this white line is 150 pixels, and this angle right here that you see with my cursor is 60 degrees. But I can drag this polar coordinate, and notice that I can make it longer and shorter in terms of distance, but I can also change the angle. And you can see how it's naturally a very radial measurement system. Now, obviously it has an X and Y position, but the information that we're dealing with is completely oriented towards a radial viewpoint. Now, the reason I mentioned the mappings a second ago is because, those of you who remember your math classes, you may recognize this as a mathematics coordinate system. We have quadrant 1 right here in the upper left, quadrant 1 in the upper right, quadrant 2 in the upper left, quadrant 3 in the lower left, quadrant 4 in the lower right. And notice that as we make the angle larger in the positive direction, we're moving counterclockwise. Counterclockwise. This is the standard graphing of angles that you will see in a mathematics course or a computation course. However, this is not how screens plot points. Let's click on this screen option right here. It looks very similar, but I want you to notice one difference. Suddenly, as we make the angle more positive, as we make it larger in the positive direction, we're now moving clockwise. So the origin axis, the x-axis where it begins is the same, but the kind of direction of the angle itself is different. On a screen, when your angle gets larger, it goes in the clockwise direction. In math, when your angle gets larger, it goes counterclockwise. These are two different mappings between polar space and Cartesian space. And there's another one that's very common as well, which is navigation. When I say navigation, I mean like ship navigation. In the case of ship navigation, the 0 value actually points straight up because you're looking in the direction out front the boat. So the 0 degree is dead ahead, and then positive angles go clockwise. These are just 3 possible mappings from polar space to Cartesian space or Cartesian space to polar space. There are an infinite number of combinations, but it tends to come down to 2 details. What is the direction of the 0 vector? Again, here in navigation, the direction is straight up. In the case of a screen, the direction is to the right, and in math, the direction is to the right. So that's detail number 1. What's the direction of the 0 vector? The second detail is, as angles get larger, do you move clockwise or counterclockwise? In math, counterclockwise. In the screen, clockwise. In navigation, clockwise. For this reason, when you take polar coordinates and you map them to Cartesian coordinates, using the superdeclarative geometry package, you can provide essentially a mapping yourself, a custom mapping. Now, all 3 of these mappings are already built into the package, but you can define your own mapping. So you can have any 0 vector you want, and you can either have angles go clockwise or counterclockwise. But that, and by the way, I mentioned some of that right in here. That's the complication. See here, polar coordinate to Cartesian, and we explicitly ask for a math orientation. Or you can ask for a navigation orientation. But the default, if you don't ask for anything at all, you're going to get the screen orientation, where the 0 vector is along the positive x-axis, and then angles go clockwise, because most of you will be working directly with screen coordinate space. So that's a very quick overview of the superdeclarative geometry package. I'll show you very quickly about how you can mess with it in code. Right here, I have actually a Dart command line app. Now, obviously, a lot of this math is intended to be used in Flutter, but as I told you before, it's a pure Dart library so that there are no unnecessary limitations. If we come in here to our pub spec, I'll uncomment the inclusion of this package. I will save. I'll do a pub get. I'll come back in here. We'll run it just to make sure it runs. We should see welcome to superdeclarative geometry, and we do. And then immediately we can say something like, we can say angle 1 equals angle dot, I guess we got to import it, angle dot from degrees 90. And let's just see what that prints out. Say angle 1, run that, and angle 1, 90 degrees. So we get a nice human readable version of the angle. anytime you print an angle, it's going to be reported the to string is in degrees, because for most humans, degrees are what makes sense and not radians. But we can also do like angle 2 equals angle from radians. Let's say, I don't know, pi over 4. And then let's print angle 2. Oops, I need to import math, save that, run it. Angle 2 is 45 degrees. And then we can say, let's say angle 3 equals angle 1 plus angle 2, because you can add angles and subtract them. And then we can say angle 3 is angle 3, run that. And they're 135 degrees. First class support for angles, add, subtract, you can multiply and divide by scalars, that kind of thing. We can also, again, create polar coordinates. So polar coordinate 1 equals polar coordinate, radius of 100, angle of, let's pass in angle 1, 90 degrees, and then we can print polar coordinate 1. Polar coordinate 100 by 90 degrees. And let's see what happens if we multiply that by 2. Polar coordinate 1 times 2 equals polar coordinate 1 times 2. And currently the semantics of scalar multiplication is that it multiplies both the distance and the angle. You can let me know if that may or may not be the most useful interpretation of that multiplication, but that's what it does right now. Of course, you could also create a new polar coordinate with just twice the distance or twice the angle and not both at the same time. But this is how you manipulate these things. Obviously, because this is a pure Dart package, there are no widgets in here. I will probably build a Flutter specific package on top of this one that adds certain radial widgets to make it easier to do stuff in the user interface based on this mathematics. But again, if you do things with dials or radial progress or things like this, you may still find that this package is a much better way to represent angles and radial positions. In fact, in this example app, for those of you who have been following me for a while, you will recognize this UI. We have an egg timer here. And so we can drag this around to a certain amount of time, and then it starts ticking down. And then we can pause it, we can resume it, pause it, reset it, all these kinds of things. I've made a certain amount of usage of polar coordinates and angles in the implementation of this dial. But there are definitely some capabilities or some requirements in a dial user interface that I think could benefit from some Flutter specific widgets. So I'll probably work on those again and put them in a Flutter specific package. But you're welcome to go check out the source code for this demo and see where I actually used angles and polar coordinates. Just like this graph here, obviously what you're seeing here is built with angles and polar coordinates from this package. Also, a really great habit to get into when you're dealing with a new package, assuming that the development team has taken the time to test things, you can use the tests as a place to figure out what the package does and how to use it. So here we have the test suite for the angle class that I created. You can come in here and just browse a bunch of tests. One thing you'll see right off the bat, useful angle constants. So I've provided, and we can jump into the source code here, I've provided a series of angle constants for you. It's so common for us to work with 0 degrees, 30, 45, 60, 90, and 180 that I've just made those constants that are always available. And because they're const, if you reference them in a bunch of places, you get compiler optimization automatically. That's something you would discover very quickly looking through the tests. Here we have linear interpolation. So angles support linear interpolation. We can interpolate, in this case, from 0 degrees to 180. At 50%, we end up with 90. So these are a bunch of spot checks to make sure linear interpolation works as expected. Value ranges. If I hadn't already said it, you would find out that angles are strictly less than or strictly between negative 360 and positive 360. Same thing if you want to represent that as values in terms of radians via negative 2 pi to negative 2 pi to 2 pi. Conversions, you can obviously convert degrees to radians, degrees to percent, radians to degrees, radians to percent, percent to degrees, percent to radians. And then inspections, things like is positive, is negative, is acute, is obtuse, is reflexive. So again, a whole suite of tests here. Same thing for polar coordinates. Adds polar coordinates together, rotates polar coordinates by angles. Angle between polar coordinates. This is a nice one to have. Calculating the angle essentially between 3 points, 2 points in an origin. That can be really annoying to do. And look at how easy that is to do here. You create one polar coordinate, and then you say angle between some other polar coordinate. Doesn't get easier than that. You save a lot of trigonometry by using a package like this. So that is a pretty quick overview of superdeclarative geometry. It should make a lot of radial-based user interfaces easier than they are. Give it a try, see if it makes your life easier. If you find bugs, please file them. If you think that some things should work differently so that the developer experience is easier, again, file issues and let me know. And again, I will probably build a Flutter package on top of this with certain widgets and classes aimed at dials and radial progress and things like that. So thanks for having a look through the package. I hope it's helpful for you, and I'll keep you up to date with any new packages that I create.